Thanks for listening to this presentation about parameterized problems complete for non-deterministic FPT time and logarithmic space. This is joint work with Hans Bodlaender, Carla Groenland, and Jesper Nederlof. So let's first talk about what this talk will cover. So first I'm going to introduce parameterized complexity, what it is exactly and why we're studying it. Then I'm going to talk about bandwidth, and the problem of bandwidth will lead us to a complexity class that we define as XNLP. I'll quickly go over what that class exactly is and why it's called XNLP. And then I'm introducing some XNLP-complete problems, and I'll go over some corollaries of being XNLP-complete. So let's start with the first. Some history of parameterized complexity. So the idea of parameterized complexity is that we study problems that are MPE hard, so they're hard to solve. However, we hope that if we fix some parameter, that then the problem is easier to solve. So the smaller the parameter is, the faster an algorithm for the problem should be. And with this, there's a complexity class that's called FPT, which stands for fixed parameter tractable. And in that lie all the problems that can be solved in time f of k, so some function of k, and then polynomial time in n. So the dependency of n is not exponential, but only polynomial, and then there might be any kind of dependency on this parameter k. There's also another class that's called XP, and in that class, everything can be solved in n to the power f of k time. So that still means that whenever k is a constant, so k is the parameter, whenever k is a constant, this is actually polynomial. But as you can see, this is way worse than having the polynomialness of n being independent of k. So this class XP lies around FPT. So everything that is in FPT is also in the class XP. So an example, vertex cover lies in FPT. And with vertex cover, I mean it's parameterized version. So then we look for a vertex cover of size k. And so we can do that in roughly 2 to the k time. So, and then some polynomial on n, so that lies in FPT. Problems that do not lie in FPT are, for example, independent set. So we can't compute it in this time where k in this case is the size of the independent set. And another example is a dominating set where, again, k, the parameter, is the size of the dominating set. So actually this picture is not complete. There's a whole hierarchy between FPT and XP. And this was introduced in the 1990s by Downey and Fellows. And it looks like this. So there's this complexity class W1 and then this W2 up until WP. So for those who know these complexity classes, this will probably look familiar. And for those who don't worry, you'll not miss that much of the talk. At least what you should know is that the inclusion works like this. So you have FPT, which is the best possible, and then it all lies within this class XP. So the problem I want to start with today is bandwidth. And bandwidth is the following problem. We're given a graph and a parameter k, and we want to permute the vertices. So we want to give the vertices a number 1 up until n, such that for every edge in the graph, the two vertices that lie on that edge actually have numbers that are close to each other. So you could see this as the reordering of symmetric matrices such that the non-zero elements are around diagonal, which is beneficial for some types of other algorithms. So for example, you might have this symmetric matrix, and then by reordering the indices, you could get something that looks more like this, where you can see everything that is black. So black here indicates a non-zero element, And here all the non-zero elements are around this diagonal. And then how far they are from the diagonal, that's this parameter k that we're talking about. So this is roughly bandwidth. And we're looking at bandwidth because it was unknown for a long time for which class it was exactly complete. So in 1994, Bodlaender, Fellows, and Hallett claimed that bandwidth was WT hard. An actual proof for this came a bit later in 2020. There was an actual proof. So that means that it lies at least out of all these complexity classes. And in 1994, Hallett actually conjectured that it's also out of this class WP. In 2014, there was the actual first proof. So bandwidth is W1 hard for trees, proven by Draghi and Lokstanov. And then, as I said before, in 2020, Hans Bodlaender actually came up with the proof to prove that bandwidth is WT hard for all integers t. So the picture looks something like this. Bandwidth is definitely not in the dark gray area. It might be in the light gray area, but Hallett conjectures it's probably not. And it's definitely in the white area. But so far, people have not been able to prove it's indeed XP complete. And that's because there seems to be another complexity class between WP and XP. And this complexity class is XNLP. And this is the class for which bandwidth is actually complete. So this class was actually studied before. In 2015, Elberfeld et al. Studied this, and they call it NF poly F log, which stands for what a non-deterministic Turing machine can solve with an F poly time, so some function of k times polynomial of n time, and f some function of k, and then log of n space. So that's exactly how XNLP is defined. We'll get into that in the next slide. So why do we call it XNLP? So let's go back to the complexity classes that we start with in complexity theory. So L is the complexity class for which deterministic Turing machines can compute it using only log n space. And NL then stands like the L stands here for log space, and the N in NL then stands for non-deterministic log space. So that means that we just want to know if there is some computation of the Turing machine that ends in an accepting state. And there are parameterized versions of this. So the X here stands for parameterized. And so we have XL and XNL, and the parameterized versions of L and NL. And so there's this f of k in front of how much space they can use. Okay, so why is there a need for XNLP then? Well, the P in our case stands for polynomial time. And that's because of the following. This L and NL, this log space, they actually imply polynomial time themselves. However, in this case, it does not imply something like f of k times polynomial time. It actually implies n to the power f of k time. So that's where we say, okay, but what if we also restrict the time next to the space restriction? And that's how we got XNLP, and that's the class that we're looking at. So some XNLP complete problems. These are the known results. As I said before, Elberfeld, Stockhuysen, and Tenau already looked at this complexity class in 2015. And there they described this non-deterministic Turing machine problem that I quickly explained before. So there's this question of whether the non-deterministic Turing machine ends in an accepting state. And then they also found some completeness for some type of timed non-deterministic cellular automaton. And then there's the longest common substring. So in that problem, you're given a number of strings, and then the number of strings is actually the parameter. So k is the number of strings that you're given, and you want to know the longest common substrings of these strings. Our results. So we found a lot of problems that also lie in this complexity class. And what's nice about it is that the problems are from all types of different types of problems. It's not just things with strings or substrings. It's, for example, here we have scheduling with presence constraints. So there's a scheduling problem. There's acyclic finite automata intersection. There's timed dominating sets reconfiguration, log path width dominating sets, list coloring, parameterized by the path width. Yes, so all types of problems. And here's bandwidth. So this picture actually is how we were able to reduce all these problems to XNLP. So the arrows indicate a reduction from a problem to another problem. So the red ones, those are the problems that we call building blocks. And these problems, they're very helpful in proving problems to be XNLP complete. I just want to go over two of these. So I'm going to explain this chained weighted CNF-Satisfiability problem and this accepting non-deterministic, non-decreasing counter-checking machine. So that's the ones that I'm going to explain quickly, just so that you get a feeling of what types of problems lie in this complexity class. Okay, so chained weighted CNF satisfiability. So normally in satisfiability, you're given a set of variables and you want to give a true false assignment such that some CNF formula is true. And now instead of just having one set, we have R sets. So we have a number of sets for each two sets that lie next to each other. So we have a formula for x1, x2. And with a formula, just so you know, it really looks like a CNF formula, so something like x11 or x21, and of course we want it to be true in the end. And then x2 then also has a formula, but then it's related to x3. So there's another formula, and that's related to x2 and x3. And then there's a formula that's related to x3 and x4. And there's a formula related to x4 and x5, and that all the way continues until the end. So there are r-1 different formulas, and they all need to be true in the end. But there's of course a parameter, and in this case, the parameter k is the number of true assignments per set. So in the example that I made here, the green ones are the ones that I set to true, and there can be at most 3 in each of these sets. So k in this case is 3, so you can set at most 3 of these variables per set to true. And then you want all the Boolean formulas to also be true. So that's chained weighted CNF satisfiability. And how you can see this is that you so if you think about XNLP, you should think about it in this type of like pathway that you decide things. So you decide something for x1, x2, and then you forget a bit about this x1, but you still need to remember x2, and then you need to decide something for x3. So you really go through the decisions like first you decide something for x1, but then at one point you can forget about it and you continue to the next part of the problem. So let's go to another problem. And this one is called accepting non-deterministic, non-decreasing checking counter machine. So this is not a problem I think you'll find directly in practice, but this was very useful for us for proving other problems to be XNLP complete. So what is this problem? Well, first of all, you're given, of course, a number k, and this k is the number of counters that you have. So these are our counters. And then these counters can not decrease. They start at 0 and they can only increase during our computation. So that's why we have non-decreasing counter machine. And then let's go to the checking part. So there are checks here. And we need to go through all the checks. So from 1, and then we need to go to 2, then we need to go to 3, and then I only made 7 here, but this list can be long. Let's see how a check goes. So if I go to the first check, it says that C1 cannot be equal to 0, or and C2 cannot be equal to 0. So at least one of these two should be not equal to 0 in this case. In this case, they're both 0, so this check will fail because they're both equal to this value that it's saying. So we need to change something about our counters. So for example, we can first increase C1 to 1. So now we can go through this first check. This is going to be a good check because indeed now C1 is not equal to 0. So we can go to the next check. And the next check states that C1 cannot be equal to 1 and C2 cannot be equal to 0. So either C1 needs to go up or C2 needs to go up. So in this case, I'm just going to increase C2 to value 2. So I can increase as much as I want in between these checks. I can even increase multiple counters. But every time that I stopped increasing counters, then I need to then I go to the next check, and so these things, at least one of these things, needs to not be equal to what it's saying. Okay, so we go through and we go to check 3. So it says C1 not equal to C1 equal to 1, C2 equal to 2. So that's the case. We need to change again something. So let's increase C1 to 2. And then, yeah, I think you get the gist of it. We need to increase things up until all the checks are completed. You can't increase up until a certain limit. So there's also a limit on the numbers of the counters. So, for example, in this case, I said the counters can go up to 2. So this is the problem. You're given these checks. You're given the number of counters as a parameter. And you're also given a bound on the highest number on these counters. And the question is there some way to increase these counters such that you go through all the checks in the right order and they all accept? Okay, so let's go through some corollaries of XNLP-completeness now that you maybe got a gist of what the problems look like. A consequence of being XNLP hard is that it's WT hard for all T and N. So you already saw that at the beginning of the presentation that this complexity class XNLP, all these WI classes lie in XNLP. So this should definitely be true. But why I'm telling you this is because it strengthens some of our known results. So for both these two results, they lie in some WT class, but now we actually lift it up to being WT hard for all T at once. It might be easier to prove that something is XNLP hard than it is to prove something that's WT hard for all T and N. So that's especially the case with bandwidth. So that's one of the corollaries of being XNLP hard. And then there's another one, or there might be another one, I should say. So there's a conjecture by Filipsuk and Bruchner in 2018. And they said that longest common subsequence has no algorithm that runs in n to the power f of k time, so that's xp time, and in f of k n to the power c space. And if that corollary is true, because longest common subsequence is XNLP complete, we actually have that no XNLP complete problem can have such a time space algorithm. So as soon as you see a problem that has a natural dynamic programming time with dynamic programming with this time, but smaller space, so something that's polynomial in n space, and then you might wonder probably it's not going to be XNLP complete if we believe this conjecture. So that's all I wanted to talk about this complexity class. So thank you for tuning in, and I hope you have a nice day. Thanks.